So what we do is
Before we go there, can I ask about interpreting the Gaussian that we derived previously?
What about it?
Yeah. So two things. When we say the initial density is the delta function, is that in k space or x space? And if
X
so,
space.
what?
It's written in X space.
Okay, but we're integrating over k's.
No. I mean, it was a trick. We went to Fourier space because we know that Laplacians, because of translation, assumed translation invariance of problem, the Laplacian gets diagonalized.
Okay.
So it was just a mathematical trick. There are natural coordinates for this problem, which Fourier discovered, which is if you do the, they did it as voodoo because if you do this transformation, it's legal because you check that it's legal, but it makes Laplacian diagonal, then you solve it there, and then you put it back into the my coordinates, which are x coordinates, and there it looks like this.
Okay.
Now,
I think that makes sense. Yeah. So basically, you're saying we just start with all of the density, like bundled up in one location, and then
but
my next question is
all the time in the Professor Zangbo's distinguished course because whenever you're solving any Green's function problem, that's what you're doing. You're saying if I know how to do it for one charge, electromagnetic field is linear problem, so it doesn't care how strong my field is. So if I solve it for one charge, I can then write the density of charges and the same solution applied to density. Sorry, go ahead.
Okay, yeah. So that leads to my next question, which is just tracing the evolution of the Gaussian in time. So from the expression, we can deduce that as time goes on, so as t increases, the decay of the exponential decreases in magnitude because the slope of the Gaussian is decreasing. So it's
the variance is increasing. So as time goes by, you get always a Gaussian, but of larger and larger width.
Okay. So that's all.
And the limit is hard to describe because the limit is, it goes constant, but very small because it's an infinite space.
Okay. Yeah. And I mean, maybe this is a whole different topic, but that also is what happens in quantum mechanics when you model.
No, you're perfectly right. So, the beauty of mathematics is that if you have a sine of theta and you replace theta by I theta, you get an exponential. So, if you know how to solve diffusion problem on a line and you decide the time should be imaginary, mathematics doesn't care. And it turns out, that is a solution of harmonic oscillator in quantum mechanics. So the simplest Schrodinger equation of, particle moving in a harmonic potential, that's what our people do in the ground floor in their experiments with heavy atoms in cold atom physics. They put them in shallow potentials. Then it's called Schrodinger equation, and solutions are wiggles. They're called Hermite polynomials with little sines and cosines stuck to them. But basically, probability of the particle in a Hermitian potential in Schrodinger equation is a Gaussian probability, and the different eigenvalues have different numbers of wiggles. So it's 1-to-1. So, so this is always the eternal fascination between is quantum mechanics stochastic or not? Do we understand it in this way? We don't. But formally, on the level of this problem, Schrodinger is equivalent to, this has many names, but let's say, doesn't matter what name I mentioned that. They're equivalent. The problem gets to be harder when you have nonlinear interactions. We have, here I'm assuming just the diffusion. But if I have nonlinear terms, things are colliding and I cannot ignore it or they're interacting, then it becomes less obvious. But, there are two kinds of integral description of such problem. One is called Wiener integrals, and this is when you have interactions, generalizes this, but for stochastic processes. And everybody understands Wiener integrals. It was a wonder kid who was not allowed to go to Harvard because he was Jewish. He was not allowed to be hired. So he had to be hired by MIT. And he invented all kinds of amazing things. But this little wonder kid, described what we now call, stochastic path integrals or whatever. Wiener integral. Now Feynman, another wonder kid who was a student at MIT, undergraduate student, he understood quantum mechanics in the same way as a random walk, but now as sines and cosines rather than a particle random walking, because you have wave mechanics. And that gives you path integral description. And that one is very contentious. People have a hard time defining path integrals in quantum mechanics because there are sines and cosines and adding up lots of them, all wiggling and being of order 1 is not trivial. So everybody understands Wiener. Everybody kind of accepts path integrals because they work very well, but they come from this observation that you just mentioned. It's Schrödinger equation in imaginary time than real time.
Okay, I was actually going to ask about the free particle case, but I guess it works for harmonic oscillator as well, because you have to model a photon as a Gaussian packet.
Well, no, in quantum mechanics, free particle is a little bit too trivial. It's just a bunch of Fourier modes. And, you might stack some spin structure on it. So every old person who has done something and, maybe got a Nobel Prize for that something, eventually has to sit down and explain quantum mechanics. And they all derive a free Schrödinger equation for particles from symmetry principles. No matter what you decide, space-time is random dots or it has to have Poincare invariance. You always describe free particles. Now, the moment they start interacting, and harmonic potential is basically free. I mean, it's quadratic potential. You're doing Gaussians. You know how to compute Gaussians. So it comes in harmonic potential.
I think there's a difference.
Then they have to derive. What do you say?
I think there's a difference because the free particle cannot be, I guess, permanently localized. That makes any sense? Because the Gaussian you use if you use a Gaussian to model it, it will disperse over time. But
if you say I have a wave function or density of free particles, they will disperse like this Gaussian disperses.
But a harmonic oscillator, because of the form of the potential, keeps it.
It doesn't disperse, and I will try to get to it today.
Okay.
And it's very. So what happens is that free particles, they're just like cats. They go all over the place. Gone. Now, I don't know. Things bound in harmonic potential, they're like rats, they're together. They can get really away from each other. And that equation is very easy to solve, both in quantum mechanics. In quantum mechanics, this gives you, familiar spectrum. It says, I have k squares all over the place. And those are kinetic energies of particles. And what they do in stochastic calculus, they give you, equations saying that you're confined, that you have width, and that width depends on how strongly you jostle. So diffusion tensor is still there, but it has to find the potential. And you find out that if I have a harmonic potential and I put lots of noisy stuff into it, it doesn't spread, but it has Gaussian distribution and non-leading eigenstates of the operator give you, various decays rates of how, if I start with non-Gaussian distribution, how fast will go Gaussian, stuff like that.
Is that question? Is that related to the Louisville's theorem? If you're familiar with that.
Louisville theorem is a special application where you have an additional constraint called phase space conservation. So in mechanics, this is more general than mechanics, but in mechanics, Louisville theorem will say that the area of this neighborhood doesn't change.
And is that because you're not factoring in noise and it's is it linear? Are those the assumptions you're making?
Yeah, linear is important. And now the symplectic structure is a mystery. This is a fact about Newton's equation, which is very dramatically explained in Hamilton's formulation, where you write acceleration, second order in time, as two equations, change of position and change of momentum. Those are Hamilton's equations. And then you realize, as Hamilton did, first, that you can get his equations by taking derivatives of a function, energy function, or Hamilton's function. Number one. Number two, that has symplectic structure, meaning there's a minus sign there. And that minus sign says that every small volume, means linear approximation to the neighborhood, has a property that things get rotated and stretched, but the area of it, at least in two-dimensional case, volume in the dimensions doesn't change. So it's a special thing about mechanics. Mechanics has a symplectic structure. And I told you that three kinds of invariants, classical groups that preserve length, groups that preserve unitarity, so length of a complex vector, and then out of the left corner, groups that preserve symmetric two invariant, or symplectic invariant, and they just show up as possible group theories. But kinds of groups, symplectic groups, but they're actually the ones chosen by mechanics, classical mechanics.
I think this is exactly Brownian motion, when the students are the particle and they slowly but surely diffuse out of the class. So I think many.
My exposition is Gaussian by definition. The more I tell you, the more confused you are, and your learning is on average 0. And so we are all, at its largest statistical forces. But I will continue in ballistic mode for a little while longer. And again, this week I'm just giving you, whatever you do, it's great. I don't expect you to know all this stuff because it's too much. I just want you to have a memory in your future that when there is noise, I should go and look at these notes again.
The noise is crucial because it helps us give us because we know that noise is Gaussian, so it gives us information about the particle. That's why it's so.
We know Gaussian in retrospect, but all these arguments I've been giving you for the courses that really Gaussian is the most natural thing about noise. Even when it's not Gaussian, the dominant behavior might be Gaussian. So even though the probability distribution has skewness, kurtosis, other properties. The peak of it, as you said last time, the large number limit. There's the essence of it is kind of Gaussian. And it's kind of cute because, this course is in linear algebra. And it turns out that taking a square of something is also linear algebra. In this case, you're looking at symmetric matrices called covariance matrix. So we get into things that are slightly nonlinear, but we know they're linear because they're related to harmonic oscillators, and now they're related to noise. So when you have Laplacian with the right sign things oscillate, that's harmonic oscillator. When you have it with the wrong sign, that's called diffusion. All of these things are very important. And they help you understand general, nonlinear, complicated properties of falling into a black hole, whatever you need to do. But you have strong nonlinear deformations as well. This is still essential in understanding all these things.
So you mentioned two types of noises. First of all, from the collision of particle, and the second one from numerics, or maybe errors. So those are not related?
So I tend to lump them together, but a careful person, that's why there are professors of probability theory and professors of economics and professors who teach you how to do hedge markets, etc. You have to go into details of what's observational noise versus intrinsic noise. But for purposes of level of understanding we have today is that any noise leads it to Gaussians. Just does. And basically it has to do with this maximum entropy.
Yeah, that's what I want to ask.
If you know nothing except you want it to be noisy, and you have basic properties, it has to be normalizable density, it has to have mean and width, you find out that if you have no additional information would decrease your entropy. And on entropy, you'll always multiply entropy by Gaussians, and that's why they're there. They're also there because it's the only integral we know how to compute. We don't know how to compute anything else but a Gaussian.
It's funny.
I mean, it's not quite true, but the special cases are not as illuminating as the Gaussian. The first thing we know how to compute is linear problem. It gives us either oscillation or exponential. Then it turns out we can do the next one by the same tricks. But now the solution is either Gaussian or weakly Gaussian, which is a wave function times every polynomial. And beyond that, life is hard. You can be working at age of 90 every day thinking about it, and you still haven't gotten it, like poor Roger Penrose, who never got it. He only started at age 27. You're way ahead of him.
Can you make a comment about...
And he was never serious. He's a screwball, and you're serious people. What?
Those are the best people, the ones who did a few years of work, like Einstein. I don't know if Penrose did that, and then they just enjoy the rest of the time.
Well, but Penrose keeps producing good work all the time, but not on level of Einstein, who had a burst which is better than average. Very good year, Then he got screwed up because Nobel Prize and being an important person, etc. Really slows it down. The other people about him, people who had some success in science, is that they feel that now they have to do important problems. They can't do nonsense. Now that's, that's bell of death. And Penrose doesn't feel like he has to do an important problem. He just has to figure out how to do quantum mechanics correctly.